For any bridge or crane girder, load is applied on the structure from a moving vehicle, and as location of the vehicle change over time, we need to find out the critical load position which provide maximum result. Though this seems like a complex process, do you know how easily we can consider a vehicle movement over time for analysis and compute the critical condition for supporting structure? Hi, I am Surajit Ghosh, and in this video, I will discuss about moving load and different options available in STAAD to apply a time-dependent load. STAAD is well capable of handling this type of load for analysis, and there is a moving load feature available to generate all possible load condition. But to consider a realistic condition and get the worst effect, we need to combine this generated moving load with other load or loading component like dead load or horizontal and axial load component. This combined load is critical for the stability and performance of the entire structure. Before going into the details about this load generation technique, I want to discuss what is a moving load and how it impacts any structure. For any gravity or lateral load, we assume that the point of application remains constant over time. For example, self weight of a floor panel is applied as an area load over the entire panel, and at any time, this load application area remains same. For imposed load, though it is linked with the usage and occupancy which might change over time, still we apply this load over the entire usable area or consider skip loading with fixed pattern. None of this load application point or zone is affected over time. Similarly, if we consider any lateral load like seismic load, we assume that the load is acting at the floor level where the mass is lumped. During analysis, we keep these application points constant and find out the critical effect due to various load combination. For bridge or crane girder, loads are generated from a moving vehicle or crane. Hence, the application points are not constant. It changes over time. For a crane girder, normally the crane starts from one end, move to the desired location, then either proceed in the same direction or travel back. If we consider this type of movement and corresponding load application on the supporting structure, for example, a truck moving on a bridge, we can notice at startup time or t equals to 0 second, it starts the journey with load applied at the extreme end. Then over time, it proceeds to other end. And finally, at t equals to n second, it completely crosses the structure and applied load intensity is back to 0. So over time, position of the load change, though the load intensity remains same at all point. How the structure is affected when the load position change? Consider this simple frame structure with multiple bays. Load from 3 wheels with different axle load is applied on this frame. Multiple load cases are generated to capture the movement of the load from one end to other end of the entire bay. These loads are generated using a custom tool. I will discuss this later. For now, check the bending profile of this girder. As the load moves along this structure, moment and deflection profiles change, and it not only affects the loaded bay, entire structure is affected due to the load transfer mechanism. This might not be true for a bridge deck with expansion joint and bearing support, but for a continuous crane girder, this is very common. For this entire movement of the load, there are few application points which generate the maximum bending moment or deflection, and these positions are required to design the structure properly for strength and serviceability condition. Now the question is, how we can determine the critical load position and if there is any alternate way to bypass this calculation. If we apply same wheel load on the entire bay, that is not an economic solution. We can also apply an average load on the structure, but both of these approach will produce highly overestimated design result. There are few manual approach like influence line diagram, using which we can calculate the maximum shear, moment or reaction considering different position of the load. Influence line graphs the response of a member as a unit load travels across it and helps to find the critical load position which generates maximum result. It is an approximate approach, and if there are multiple loads moving in different direction, it does not provide an accurate result. The best solution is to go for an accurate analysis where we can capture the complete movement of one or multiple vehicle on the structure and find out the most critical condition by reviewing the analysis result. And this can be achieved using moving load analysis. Application of moving load is not only limited to bridge or crane girder analysis. There are several other conditions when we need to consider a time-varying load, like analysis of an elevated station building where one or multiple trains can move from different directions. This is one of my old projects on metro station building design. In this model, I have considered a moving load to calculate the critical condition which is used later for design of slab and beam. Similarly, for a conveyor belt structure or any structure used in a plant to support material transportation trolley, we need a detailed analysis considering moving load. How to apply this load correctly and consider all load components like vertical, horizontal, and axial thrust during analysis? STAAD has a moving load generator, but how we can use this to consider horizontal components and combine the load with other load cases? That I will cover in my next video. Stay tuned.